Hello, this is Physics Chapter 6, Lecture Number 2. In this lecture, we're going to cover the On Your Own problem 6.5 through 6.7. In your book, we're going to be looking at probably where you want to turn to is page 193. All right, page 193. Think of this, we can call this, if you want, the seesaw lecture. Because if you ever played on a seesaw as a kid, this will make a lot of sense. So, with translational motion, so we're on page 3 of your notes, translational motion, that doesn't involve repeatedly passing the same point in space. However, with rotational motion, which is what we're going to talk about today, you have motion around a central axis, and the object could repeatedly pass the same point in space. And the axis of rotation is the point in space that is at the center of rotational motion. All right, so in the case of, on page 193, we have this picture of a wrench and a nut, and the axis of rotation, what the wrench is rotating around, the central axis would be the nut there. Okay. Now the lever arm is the distance from the axis of rotation to the point at which a force is applied. All right? So distance. Lever arm is just a distance. So if you will flip back to page 191, you can see that the lever arm is the distance between the axis of rotation and where the force is applied. And it's the perpendicular force. Okay, so if you were to yank on that wrench, not perpendicularly but at an angle, then the x component of the force is wasted. It's only the y component that's perpendicular to the axis of rotation is what counts as a force. All right, so that brings up torque. The length of the lever arm multiplied by the component of the force that is applied. We'll do a torque equation in just a minute. And just like I said, only the component of the force perpendicular to the lever arm contributes to the torque. Okay, so I've got a space for you to write the torque equation. For torque, we use the Greek letter tau. All right, you have to memorize that. And it's equal to the perpendicular force, so there's our perpendicular symbol, times the lever arm. So torque, we've been using force, so I'm not gonna write that down, but and then R is the lever arm, which is just, lever arm is just a length. Okay, so we have force times distance. So our unit for torque is going to be Newton meters, pounds times feet. Okay, any force times distance will work, but that's mostly what we're going to be using. The two most famous torque units are Newton meters and pound feet. We might end up going with Newton centimeters, pound inches, whatever. All right, and then finally, increasing the torque on an object increases its rotational acceleration. All right, increasing the torque increases rotational acceleration. So let's take a look at our first on your own problem involving torque. On page 193, it says a father and daughter are trying to change a tire on a car. The father attempts to unscrew the lug nuts with a small 12.3 centimeter wrench, and is capable of applying a 612 Newton perpendicular force. The daughter, on the other hand, can only deliver a 214 Newton perpendicular force. If she chooses a longer wrench, 41.1 centimeters, is she or her father more likely to get the nuts unscrewed? Okay, well, let's just figure out the torque for each one. So for the father, the torque, that's not a good tau, is it? That's just a T. There we go. The torque is the force, 612 newtons, times the distance, or lever arm. I'm going to go ahead and change it to meters, 0.123 meters, so we can get it in Newton meters. You don't have to answer the question, but that's 75.3 Newton meters. And then the daughter, her torque, she only has, roughly a third the force, 214 newtons. But she was smart enough to grab a longer wrench, 0.411 meters. All right, remember to divide centimeters by 100 to get meters. And that's 88 Newton meters. So it's actually the daughter that's more likely to get the lug nut loose. Okay. So going down the notes, this is just, we're going to set a standard that torque that causes clockwise motion is considered negative. Counterclockwise is positive. And if you are in rotational equilibrium, that's the state in which the sum of all the torques is 0. All right, and I say in your notes to look at the illustration on page 195. We've got a couple of kids on a seesaw. And if you've ever played on a seesaw, there's a point where you can sit on it on each side where the seesaw will just sit still, right? You'll just kind of float there. You can't stay in the exact same spot in order for that to happen unless both children weighed exactly the same. But this one is showing to be in equilibrium. All right, the seesaw's not moving anymore. The boy is heavier and he's sitting closer to the fulcrum than the girl, but it's hit an equilibrium state. All right, let's work 6.6 and 6.7, and we will be finished with this lecture. Very short. So 6.6, flip over to page 196. All right, 6.6 says, 2 children play on a seesaw. One weighs 221 newtons and sits 1.12 meters away from the seesaw's fulcrum. If the other weighs 171 newtons, how far from the fulcrum must she sit in order to balance the seesaw? All right, of course, usually the seats are exactly the same distance from the fulcrum, so this is an odd situation here, but I'm going to go ahead and draw this out. So we've got a fulcrum. We have 171 newtons. And then over here, 221 newtons. And the distance is 1.12 meters from there to there. And we want to know this distance, x. So the sum of all the torques has to be equal to 0. All right, so torque, of course, is the force times the lever arm. The force is just going to be the weight in this case. So we would have, really what you do here is set the two sides of the fulcrum equal to each other. I'll go ahead and do it for the first time. We've got 171 newtons times x plus 221 newtons times 1.12 meters is equal to 0. But that's essentially what you're doing, is you set one side equal to the other. This is going to cause, this one it would be negative because that would be a, this one would be positive. This one would be negative because it's causing a, going this way, a clockwise torque. But it's much easier just to set the two sides equal to each other. So set the two sides of the fulcrum equal. And then you don't have to worry about the signs, which one's positive, which one's negative. So I'd have 171 times x is equal to 221 times 1.12 meters. So x is equal to 221 newtons times 1.12 meters over 171 newtons. All right, and that is 1.45 meters. And I hope that makes sense. The girl, because she weighs less, is going to have to sit farther away from the fulcrum than the boy in order to achieve equilibrium. All right, pause video if you need to, and we'll do 6.7. All right, 6.7 is on page 197. So here we've got a balance system where we have 3 kilograms and it's 45 centimeters to the fulcrum. And then on the other side, I've got X kilograms, I don't know how much, but the distance to the fulcrum is 75 centimeters. And it asks for the mass. Well, since both are in kilograms, we don't have to change this to weight. We don't have to change it to newtons. We don't have to change this to meters. Okay, we're just getting a ratio. Unless it asks specifically for meters, or if it asks specifically for newtons, then you would need to change it. But we're going to set the sum of the torques equals 0, set each side of the fulcrum equal to each other. So we've got 3 kilograms times 45 centimeters is equal to X kilograms times 75 centimeters. All right, and if we had, maybe we had 2 weights on this side, then we'd add the second weight and distance, okay? So that's going to be 3 times 45, so X, just solving for X, is going to be 3 kilograms times 45 centimeters over 75 centimeters. All right, so the mass should be smaller because it's further away, so you would need less mass. You have more of a torque on the right side than the left side, don't you, if you were to move it up. So that is going to be 1.8 kilograms. So because it's further away from the fulcrum, you can have less of a mass to achieve equilibrium. All right, that's it. So the homework related to this lecture is going to be review questions on page 214. You can do 5 through 9, and practice problems on page 215. You can do 4 through 7. All right, so not really a very difficult section, so enjoy.